Here we're going to look at what happens when we take a conjugated diene and react it with an acid like HBr. So we're going to stick with one equivalent of acid, and just to give you accurate percentages, I'm telling you what temperature this one is carried out at, but we will discuss temperatures further here in just a bit. So the first thing you want to do is actually find the diene portion of your molecule. Here are the 4 carbons. That's part of the diene. Now in this case, we have a symmetric diene, meaning there's a plane of symmetry that runs through it. I'm going to number the carbons of the diene. Okay, so let me show you what the products are, and then we'll try to figure out how we get those products. Here's our 2 reaction products. We end up with one product where the H is added to carbon 1, the Br to carbon 2, and our second double bond just stays between 3 and 4. That's in a 65% yield. We end up with a second product where the hydrogen's added to carbon 1, the Br to carbon 4, and the double bond actually moves between 2 and 3. And these products are given distinct names. The product where H and Br are added to 1 and 2 is called the 1,2 addition product. The product where the H and Br are added to carbons 1 and 4, that's the 1,4 addition product. So we have a couple of questions. The first is, why does the hydrogen end up on 1, Br on 2, but not vice versa? Why don't we get hydrogen on 1 and Br on 2? Because both would be secondary carbocations. The second question we want to ask is, why do we get the 1,4 product at all? Because that includes what looks like a lot of rearrangement. So anytime we're trying to figure out why we get certain products, there's always a consistent answer, and that's going to be to look at the mechanism. Okay, in the mechanism, we're going to start with our diene and react that with HBr. And we always start at our double bond between carbons 1 and 2. Now, if this were an unsymmetric diene, we would actually have to number this twice and do 2 different mechanisms to figure out all the different products. But it doesn't matter here which side we number from because of the symmetry in the diene. So we're going to start between 1 and 2. And we'll put our pencil down on the double bond, draw a curved arrow to the proton, and we lose the Br from that. So let's draw what we get. We're going to put the hydrogen on carbon 1, and that gives us a carbocation on carbon 2. So one of our first questions was, why don't we get the hydrogen on carbon 2? Well, the reason for this is, even though we would consider this a secondary carbocation, it's not just secondary, but it's actually secondary allylic because it's next to the double bond. And what does the secondary allylic carbocation have? Resonance. That resonance stability actually trumps the Markovnikov rule that we typically see. So let's go ahead and draw the other product that we don't, or other intermediate that we don't get. Just to make sure we're fully aware. So if you were to put the hydrogen here and get the carbocation here, that's just a plain old secondary carbocation. That doesn't have any resonance, so we're going to eliminate that as a possibility. Because this first structure does have resonance, we need to draw both resonance structures. Okay, so for resonance, we're going to use the pi bond, move that toward the carbocation. Let's go ahead and put our numbers in just to make sure we don't lose track of things. We still have the hydrogen here on 1, the double bond, move between 2 and 3, and the carbocation is now on carbon 4. So now we have both resonance structures drawn. Once you have both resonance structures, from here we can draw the products if the Br adds to each. So start with this top resonance structure. If the bromide ion adds, here we get the 1,2 product. Likewise, if we were to do the same thing with our other resonance structure, and add that to the carbocation, we have the H at carbon 1, the Br at carbon 4. This would be a 1,4 product. So that answers our 2 fundamental questions. The only other thing you might be wondering about is, why do we get a higher yield of the 1,2 product? So the 1,2 was 65% versus 35% for the 1,4, at least under these conditions, and that's due to what's known as a proximity effect. So what's actually happening in the reaction flask is the HBr has to come in close proximity to the alkene. The alkene will react, and when you form that carbocation, the Br is already close by. So as soon as that carbocation is initially formed, this bromide is still up here close to where it left the hydrogen. So it's in closer proximity to carbon 2 than it is to go down here all the way to carbon 4. So that's why it more easily attacks here and gives a higher yield of the 1,2 product.